Welcome to approximating area under a curve. So an introduction to area under curve. Before integration was developed, people found the area under curves by dividing the space beneath into rectangles, adding the area, and approximating the answer. As the number of rectangles n increases, so does the accuracy of the area approximation. So we're taking a step away from antiderivatives. But you'll see later on how these two things, area under curve and antiderivatives, go together. All right? But let's just look at area under curve for now. So by the extreme value theorem on any interval AB, f contains a maximum value on AB and f contains a minimum value on AB. So if I'm looking at an interval, so notice there we're looking at the interval 1, 2. We see there's a maximum, 1 point there is a maximum, 1 point there is a minimum. And it happens to be the maximum's at 1 and the minimum's at 2. And I think I have that. Did I have that on the next page? That's a different graph, or let's just put it over here. So right here we have a maximum. That's the maximum value of the function. There we have a minimum value of the function. And we will be looking at closed intervals. It has to be a closed interval that we're finding the area under the curve, because we're finding area. It can't just keep going on forever. What's infinite area? That has no meaning. And I'm waiting for the page. So if we divide an interval into n subintervals, we could call each one the ith interval, right? So that just means we have a first interval and a second interval, and we're going to keep on counting, right? Because we don't know how many intervals it's going to change for each problem, we'll just call it the ith interval so that we have a way to talk about it, because it could be a different number each time. The maximum value that f reaches on the ith subinterval is called f max. The minimum value that f reaches on the ith subinterval is called f min, or fm, f little m. All right, so there's our interval 1, 2. Yeah, that is the same graph. Sorry, but that's okay, because I pointed it out on that graph as well with those 2 points there. So here we have a rectangle. So maybe when I draw my rectangle, I'm going to let the height be the minimum value, right? Because it has to be a rectangle, right? We're using rectangles to approximate area here, because rectangles are easy to find the area of. So we call this an inscribed rectangle. Inscribed means that it lies inside the subregion, right? So notice none of that rectangle is hanging off the curve there. It all fits inside the curve. It's all under the curve, right? And the curve, by the way, is going to the x-axis, right? That's our stopping point, right? So if we call the x-axis one boundary and the curve the other boundary, you can see the rectangle is within, it's inscribed, it's within that curve there. But maybe I don't want the minimum value. Maybe I want the maximum value. All right, so now I have a circumscribed rectangle because I want my rectangle to end at the largest value in the interval. So my f little m, f min, was 1.6. So if I use 1.6, that will be the height of my rectangle. If I decide to use the maximum value, it's going to be 2.75. It's going to be the value of the function. And that's for the same interval. We can't use both. We have to use one, or at least when we're dealing with rectangles anyhow, we have to use one or the other. Either it's going to be an inscribed rectangle or it's going to be a circumscribed rectangle. Or maybe it'll be a little of each. So but that's later to come. Finding the area of each region is easy with rectangles, because rectangles super easy. It's just the area of a rectangle is just width times height. And these areas can be added to approximate the area of the function. Here we could approximate the area under our function here between a and b, so that's going from the function down to the x-axis. Notice that the rectangles do not have all the same width, so I'd have to calculate each rectangle individually. Well, maybe it would be easier if all the rectangles had the same width. So W equals change equals delta x. That just means that the width is the change in x. And I'll put change in x. right? And the h, the height, is just the value of the function. All right, so we'd have to calculate the area of each of the rectangles and then add them up. Maybe it would be a little bit more efficient if all the rectangles had the exact same width. We just made them all the same size rather than random widths all over the place. And that's what we're going to do. We'll make them all the same width. And we're waiting for the page to turn. There we go. So what we're doing here by using rectangles to approximate the area under curve has two names. Know them both. They're used interchangeably. One is called Riemann sums, after a mathematician, Riemann. The other one is rectangular approximation method, because we're approximating using rectangles. And so I will use either one interchangeably, so no, I'm talking about the very same thing. Right? We're going to use equally sized partitions of the interval to make the calculations easier. By having bases of equal length, the base can be factored out when calculating the sum. So we can just multiply by the widths one time. We can get we add up all the heights and just multiply by the widths one time, rather than multiplying each height by the width. And it's a little less multiplying. Saves us a little bit of time. So introduction to area under curve continued. So there are three methods we can use to find the area under the curve. We are strictly looking at the first one, Riemann sums, rectangular approximation method. Later on, we'll look at the trapezoidal rule. Simpson's rule, we're not going to be looking at in this particular lesson, neither in this podcast nor in this whole lesson. Right? We're not going to be looking at Simpson's rule. Just the Riemann sums and the trapezoid rule. But right now, just focus on the rectangular approximation or Riemann sum. So for each of the method, we need to know the function of the curve. We need to know what function we're talking about. We need to know the number of partitions or rectangles. It'll make a difference. And we need to know the boundaries on the x-axis, which we are finding the area. There has to be a start and a stop, right? Area is a finite number. It has to have a finite boundary. And so you need to be given those things. To find the change in x, very, very simple. So for instance, if our interval was 6 units long and we wanted to divide it into 12 subintervals, right? Well, if you take 6 and you divide it by 12, that means each one's a half, right? So each of the change in x is just going to be 0.5 or 1/2. So if the interval is from 0 to 2 and we want to divide it into 5 subintervals, right? We take the change in our x there and we just divide it by the number of subintervals. So change in x is the length of the base of the rectangle. To find out change in x, we take the larger x value minus the smaller x value, the end of the interval minus the beginning of the interval, and just divide it by the number of subintervals. That's all there is to it. It's so simple. All right, so here we have an example with absolutely no numbers on it. So we're not going to be calculating the area or approximating the area here, but we're just going to use this to look at. All right, so here we divide the subinterval from A to B into n pieces. Each piece has the exact same width. And I had this up here earlier. I think I erased it. So that means our change in x here would just be the larger value, b minus a, divided by the number of subintervals. So each one of these has this as the width, right? Every single subinterval, every pink one and every blue one, they have that as the width, right? The end of the interval minus the beginning of the interval, and then however many subintervals it is. That's all there is to the change in x. So now we need to find the height of our rectangles. That's the width of our rectangles. And actually, can I get width in there? Probably not. Let me just write width under there. Come on, go back, go back, go back. I really have no patience when I have to wait for the computer to go back. This is the width of the rectangles. By the way, You don't have your notes, so I'm going to give you notes that have everything I've written down. So don't worry. Just watch, listen, learn. All right, so our value of the function is the height. So f of x equals the height. And the value of the function, or the height of our rectangles, depends on where we put the edge of the rectangle, because it's a rectangle and that's a curve, right? And rectangles have, are going to be, they have right angles, so it's going to be all vertical and horizontal lines, right? So it's not going to curve at all, right? So if I put these particular ones for this f of x, the height is equal to the, excuse me, left endpoint. Right? Notice all of them are on the left. So here is one value of the function. Here's one value of the function. Here's one value of the function. And here's one value of the function. And all of those values, if we add them all up, that is all of our heights. Right? That's all our heights added together. But we don't have to put it on the right-hand side. That's one way we could do it. Right? So the definite integral, the area under the curve, is approximated using a series of rectangles. Here we have the height is the left endpoint. And come on. I don't like spinning ball of death. There. So same picture, but I wanted to show you that I could do it this way. And then it goes here. So now my f of x, my height, is the right side of the rectangle. And it matches the value of the function on the right-hand side. I should probably put value of function on the left-hand side on the other slide. I'll do that afterwards. Value of function on the right-hand side. So notice these rectangles over here are not the same. I think you can actually see them right there because I've colored over the previous example. Are not the same height as the pink and blue rectangles from the other slide, which happened to also be on this slide. So I'm just going to put this over here. So the height is the left end point. And so I want to put it exactly the same way as I wrote it on the other slide, and I forgot what I wrote. It's the So value of the function may not be exactly the same, but have the same meaning. Value of the function where the rectangle hits on the left-hand side. Very mathy word there. Hits, intersects. I just want to make sure you understand that the rectangles are not going to be the same if I use it where it hits the function, the value of the function on the left-hand side. Move again, move again, move again. Come on. So it would not be the same height is if I use that. There we go. Value of the function on the right-hand side. Right. So they're going to be a little bit different. Did I make an? I don't know if I made one more picture. Yes, I did make one more picture. We have one other way we could do this. So maybe I don't like the left. Maybe I don't like the right. Maybe what I like is the middle. Maybe I think the middle is the best. Or the middle is what you're asked to find. Whether or not you think it's the best. So now my rectangles look like this. And there we go. I'm trying to draw this straight. Not measuring it. Oops. Maybe and we got a little glitch in the computer there. Well, pretend that's a rectangle. There we go. All right. So now notice the heights are different still. So now our height is the value of the function in the middle of the rectangle. And it's the value where the middle of the rectangle hits the function. Our new mathy word. But I think you'll understand that. So that's why I decided to use that new mathy word instead of intersects. Right? Where I'm drawing the line and I stopped, right? I drew those middle lines there and I stopped when I got the function and I drew my rectangle so it was right in where the middle was hitting. Okay? With the exception of the one that looks a little blipped here. This should really go a little higher like here, but yeah, it looks maybe a little better except for the little blip there. All right? So 3 different ways. Which one is right? They're all right. Right? It all depends. It depends on the function. It could be something we decide based on the function. It depends on what the question asks. If the question asks for it to go to use the endpoint, to use the value of the function on the left-hand side, then we're going to use the left-hand side. If it says use it on the right-hand side, we're going to use it on the right-hand side. If it says in the middle, we're going to use it in the middle. Right? So all 3 are correct. So I just want to introduce that to you. So now you have all these heights. Whichever way we used, that's all 3 of them, by the way. That's it. There's no new one coming up. It's either on the right-hand side, the left-hand side, or the middle. So much else I can do. All right? And we're going to take all those and add them up. All right? So here our width is just the change in x, right? The difference in the x values divided by the number of subintervals. And so we only have to multiply it 1 time because every rectangle has the exact same width. And the heights are the value of our function, right? So the 1 here, when I plug in a, I get this value. If whatever this is, let's just say it's w, right? So w is, I shouldn't say w. Let's just say, that's no other way to put it. So here I've added a little bit. I'm not at a anymore, right? I'm at a plus w. So this spot right here, I'll just put a plus w. I think that's the easiest way I can say it. So this spot here is a plus w. This is a plus 2 w's, right? I added 2 w's, right? 2 widths, right? To my a value, right? My starting value, right? I moved over 1 interval. I moved over a second interval. Boy, that's really hard to read, isn't it? That looks just like gibberish, doesn't it? A plus 2w. I was trying to write small. And then the next one would be a plus 3w, and then a plus 4w. Did I do too many? 1, 2, 3, 4, 5. It was 4 rectangles there. I see 4 rectangles. So my writing is too big. So let me point out where they all are located. A is no problem, right? So A is right there on our rectangle. A plus W is in the right location right there. A plus 2W goes there. A plus 3W goes here. Do you notice we didn't use B? B is not used. If let's call it the left value of the function is used. A is, but not B. When we use the left-hand side. Ooh, and I'm at 20 minutes already. Let me just finish up this part, and then I'm going to start a new podcast and just kind of finish going through the introduction. That's all we've done is do the introductions. All right, so I think I have this one more slide of this, and if not, I'll write it over here. And before I give this to you, I will rewrite that bottom part a little bit nicer. No, I don't have it over there. So I'm going to put it over here. I must have erased it. All right, so my area here is going to equal the width of, so it's just, let's do this. Area, right, is going to be the height times the width. Let's call it height, not length, because that's easier to think of, because these are the heights of our rectangles. Length, yeah, what's length, you know? So our area is going to be all the heights. That means it's going to be f of a plus f of a plus w plus f of a plus 2w plus f of a plus 3w, and there's only 4 rectangles there, so we should stop making those, right? That's all there is, times the width. And the width is just the change in x, or oops, b minus a divided by n. All right? That's all it is. So we're just going to add up all those heights. That'll give us all the heights of all the rectangles at one time. And rather than multiplying b minus a divided by n times f of a, and b minus a times divided by n times f of a plus w, and b minus a divided by n times, and so forth, right? I don't have to keep saying that. We just add all of them up and do it one time, right? And then we'll take care of all the whole area all at once, right? So all the heights times the width one time, and it just saves us a little bit of time. All right? And that's basically all we're doing. And now it's just a matter of what rectangles are we using? Are we using the left-hand side? Are we using the right-hand side? Are we using the middle? And what are they? All right? So I'm going to stop this right here, and I'll pick up on the next page. All right? Bye for now.